Hello, good afternoon or good morning, depending on where you are. Welcome to the 6th episode of our webinar series on R&D activities on sCO2 in Europe and beyond this time by ETN Global. For those who don't know us yet, ETN stands for Energy and Turbomachinery Network, and we are an international membership association that represents the entire turbomachinery technology value chain. And my name is Jitka Spolcova, and I work as a project officer for ETN Global. I will moderate the session together with Marco Ruggiero, who is with me, who works as a senior engineer at Baker Hughes, having more than 20 years of experience on different R&D programs. So he's extremely competent to co-chair this session. If you remember, in the past episodes, we spoke about the component challenges. So today we'll have a look at the sCO2 cycles from a little bit different perspective, and we'll talk about balance of plant. As you probably remember from past sessions, this webinar is in cooperation with 9 European R&D projects that are either EU or national funded. You see the individual logos on the screen. Once you receive the presentation, you can click on them and learn more about these projects. So there is a few things I need to inform you before we start. This webinar is recorded, as it always is. Another thing is that you probably noticed that by default, you entered the webinar with your microphone and camera off. This is on purpose for everyone's comfort. However, at the end of the session, during the Q&A, you will be able to switch them on and ask your question. So concerning these questions, as I just said, there will be a Q&A session, so you can wait with your question or questions for the end of the entire session, or if you want, you can ask the question anytime you like in writing, in the Q&A, or in the chat, whatever works for you better. As always, you will need your phone because there will be some Slido interactions. And at last but not least, you don't need to take many notes unless you really want to, or screenshots, because all the presentations that you will see will be provided by us together with the recording of the entire session. So who are the stars of today? Well, the speakers, of course. So you see that these 4 gentlemen will deliver to you their presentations, whose name you have on the screen. So they will present first, then there will be a panel session that will be moderated by Marco Ruggiero, and at the end, there will be the Q&A session that I talked about earlier. Well, and this is us, Marco and myself. I already presented ourselves. So at this moment, I would like you to take your phones because we have the first Slido question. So please scan the QR code by your phone. And in a little bit, you'll see the first question. I would like to tell you that there are no wrong or bad answers or correct answers. This is not a test. And moreover, it's absolutely anonymous. Even if I want to, I have no means to find out who answers what. So please don't be afraid and give us your answer. It will be a great introduction for the session. So I guess you are ready. So we can proceed with the first question. So what is the first application that comes to your mind when you think about supercritical CO2? I would like to ask you to try to limit your answer to 1 or 2 words. You can submit a few answers if you want, and you can also upvote other people's answers. Oh, this is great. Lots of people engaging. There are still a few participants that are typing, so I propose that we can wait still a few more moments.
As we were discussing jokingly during the dry runs, I'm happy that people have power generation in their mind when they think about CO2 instead of decaffeination. That would be been really a shame. So yeah, you are in the right place.
That's a good news. Yeah, I guess majority already submitted their answer. The general map is not changing so much. So maybe Marco, you can help me debrief the answers if this is something that you expected or maybe surprised about these answers.
No, I'm not really surprised. I mean, power generation is every application we've seen with CO2, with a few exceptions. We probably will be seeing today are no power generation applications. I'm interested in seeing the battle between CSP, waste heat recovery, and nuclear. I mean, that's very interesting. So people are looking at these three. Probably they are the three that I mean, nuclear is going in the background anyways now. But yeah, more CSP and waste heat recovery are the two that people have in mind when they think about SCO2. Which is probably what we also considered if we look back at the paper we produced back at the beginning of the year of last year for the ASME on waste heat recovery in offshore applications. So probably this is aligned with what we see. Yeah, let's wait and see what the presenters have to tell us about their own view on balance of plant and potential applications.
Excellent. So I guess we are ready for the second Slido, which, as opposed to other times, comes right now, not at the end, but right now. So please keep your phones close by. The second question is, what is the first item that you think of when BOP, so balance of plant, is mentioned? So the same thing, please try to keep your answers pretty short. Again, you can submit a few answers if you want. Now there's still a few people typing, so maybe we can wait a little bit, a few more moments. But the whole map is not changing so much anymore. So Marco, I will ask you again to debrief on what we are seeing.
So yeah, looks like people are seeing one big system, which is, I mean, a series of components that are part of the every application that we have with this one, which are the heat exchangers. It's unclear to me whether people here are thinking about the recuperative heat exchangers, primary heat exchangers, or the coolers, but yes, let's say it's not turbo machinery related. So it's not something that spins. It's something really sits there and has to do with bringing in or bringing out the heat input to the cycle. I see also another aspect which is probably more important for closed systems with an aspiration to be to have, let's say, good ramp rate, or let's say wider operating range, which is the inventory control, which is something that people usually don't consider for application, as in supercritical carbon dioxide cycles for, let's call them single phase, so non-transient cycles. This piece is very important if you want to go wider on the operating range and still be able to operate with good efficiency. What else is there that is not usual? Let me see. Probably the fact that people have identified that cooling as one of the items which might be important is a good sign, because we know from also the past webinars, but I mean, whoever has looked at the cycle, that if you are using a non-transcritical cycle, even more important, if you are looking at a transcritical cycle, you want to have your CO2 enter the compression phase close to critical point. And so cooling, not only the ability to cool to a certain point, but also the ability to control the temperature at the inlet of the compressor is critical, as a couple of degrees at the inlet of the compression phase can swing the density by a factor of 2 or 3. So that means that your flow coefficient in the compressor is going to change a lot. So you might find yourself in an inoperable condition, which is very important. Overall, it's a good collection. I mean, I've seen almost every system that we have in there, and it's funny, and probably we'll need a dedicated webinar on maybe to dive down on what is a balance of plant, because of some of what we dubbed the main components in the previous webinars are also mentioned in the balance of plant. So, but yeah, I mean, that's just vocabulary probably.
Okay, thank you. Excellent. So I think that it's good news for all of us. So what we have just seen, because it's obvious that we have a knowledgeable and competent audience. So that's a very good news. And I think that now is a good time to introduce the first speaker. So I will stop sharing my screen, because he will take this place. So the first speaker is Matteo Baggiani. He works as a business unit director of the modular EPC division for SIME Group. He obtained his master's degree in electrical engineering from the University of Pisa in Italy, and developed his career in the oil, gas, and energy industry since early 2000. He's currently in charge of supporting the company strategic development into new products and energy transition by coordinating EU-funded projects and R&D activities. So, Matteo, the floor is yours.
Thank you, Jitka. Thank you, Marco. Good evening to everyone. Well, yes, the slide was very interesting, I can say, because especially the second one gives an idea on, the term balance of the plant as a lot of generates a lot of uncertainties. Let's say like this. Actually, when we started defining these presentations, we understood, and you will see also the other participant, any one of us in the technical fields has a different idea of what is the balance of the plant, and that means that, as Marco said, a good discussion on the topic it's very important. Also, and this comes to my presentation, also because most often when you have to make a new plant or a brownfield application, most of the idea and most of the work goes on the main items, because obviously main items are, the main characters of the story, and that's for sure. Anyhow, and this is what happened in the project I will present, the balance of the plant can be anyhow a very important lateral character that can have an impact, a strong impact on the viability of the project itself. My presentation will not be very technical, will be on the other side, a view on the impacts of the balance of the plant on the economics of the project and how it can impact the fact that a project can go on or not in an industrial environment. So the project that I will talk about is the Cool Heat project. That basically is a UA-founded project. It's a power cycle and it's a waste heat recovery unit, as in the first presentation. So it's one of the main association for supercritical CO2, according to the Slido. It has been taken on by a consortium of a number of partners, enterprises, among which there is SIME, my company. And by the way, we were in charge of, let's say, making the system integration and developing, therefore, the balance of the plant. Just to have an idea of the power cycle, it's a waste heat recovery system. You can see in the right upper part the waste heat recovery unit that through a heat transfer fluid gives the heat to a primary heat exchanger. And then we have a compressor and turbo expander systems driving, a compressor, then a gas turbine that substantially drives a generator and produces electricity, and some recuperators, obviously, in the main cycle. The supercritical CO2 is circulating in the main loop in the turbine 1 and 2 and in the compressor. But what is the balance of the plant? In the second slide, we understood that there is, I wouldn't say confusion. The fact is that there is no clear definition in the term balance of the plant. I came from the electrical engineering, where the balance of the plant are everything that allows, let's say, a power generation system to be connected to the grid. Then my second part of life was in the oil and gas industry, where, using a chemical definition, the balance of the plant is everything outside what it's called the chemical train. So everything that it's around the main equipment that produce the chemical product that the plant has to produce. Let's say, so I think that one of the most important things I have to do in my 15 minutes is defining what is the balance of the plant for me in this project. And so it is composed by, let's say, first of all, the heat transfer fluid system. So what takes the heat from the waste heat recovery unit to the loop in the supercritical CO2. The inventory system that it's basically, as somebody said, let's say a storage of supercritical CO2 needed to refill the fluid, or also to store it in case of different boundary condition of the system itself. It gives stability basically to the power generation system. A lot of auxiliaries, everything that is around the main component to make component works. So compressed air, nitrogen, cooling water, all the electrical auxiliaries, the control system itself, and the firefighting. And obviously, mechanically and electrically, all the interconnecting around the main equipment. So everything that is colored in this slide, it's what is balance of the plant for me, and maybe it's not the same for all everybody that is joining this webinar. Okay, so discussing about everything that is around the main components means discussing about a high percentage of the work and of the capex that has impact in a power cycle and in a project itself. Not only in terms of, as I said, in terms of cost, but only in terms of feasibility. What I will do is I will show you 2 examples of the impact, economical impact, and not only of the balance of the plant in 2 real cases that we investigated in this Cool-It project. Okay, our idea was to install our let's say TRL7 power cycle in a demonstration plant. And due to, let's say, some thermodynamic facts, the best solution appeared to be cement plant. Okay, cement plant that has many criticalities. And some of these criticalities has aspects in the balance of the plant. So the first thing we have to understand anyhow in waste heat recovery system is that most of them has to be installed in existing plant. Also because the waste heat recovery system based on supercritical CO2 goes to are applied to let's say an additional percentage of waste heat recovered, not to the main recovery in general. So let's say all the cases we investigated, most of them, 99% of them are brownfield application. When you go to brownfield, that means, you know, existing plant, you have a congested footprint because the plant is already full of things, equipment, other waste heat recovery unit, anything. You deal with all the infrastructure, specifically from the electrical point of view, and as we said, we are talking about power generation, and the electrical grid, the electrical connection is a plus, are needed in this kind of plant. There is lack of water availability. It means we have some problems for cooling. Cooling was one of the words that appeared also in the second slide, by the way. And obviously, difficulties in tie-in location. Where should we put the waste heat recovery unit? Where should we put in general, our plant? So designing the balance of the plant can actually make the real difference between having a viability, economic and technically, to make a project or not. So just 2 examples. The first one is a cement plant in, let's say, in the middle of Europe, in Czech Republic. The idea is to put our plant in this area. So the circular red dot is where the waste heat recovery unit should be put. Basically, it's in a duct rising from one part of the cement process. Actually, the plant was in such a condition. I mean, it was very congested and also placed, as you can see from the picture in the bottom left area. Actually, this green part is a small river, okay, and the only that was there, we can do nothing about this, and the only part that was available to host our power cycle and all the ancillaries around him was the squared red, let's say, rectangular area that was on the other side of this small river. So even if the piping connect, the CO2 supercritical cycles has an important characteristics that they have a very reduced footprint and small pipes going around the plant. That it's a plus. Anyway, in this case, even if the pipes are so small and the footprint is so small, the fact that we had a river inside the plant forced us to take them far away from the waste heat recovery unit. This implied, a number of things that jeopardize our project. Basically, they need to maintain the heat during the transfer of the heat transfer fluid from the waste heat recovery unit to the plant. They need to make an erection of a high structure to sustain the pipes, that even if they are small, still they need to be, sustained. And we will see later what the impact of this 60 meter and this jumping over a river had on the project itself. The second example is another cement plant. It is in Italy. Luckily, in this case, we identified a tie-in location and a position of the power cycle really more favorable than the previous one. You can see there are only 20 meters between the power cycle and the waste heat recovery unit, nothing in the middle of it, a wide area even bigger than what we needed to install the power cycle nearby. And moreover, as you can see in the right part, there are many auxiliaries already in place around the area of the power cycle. So firefighting equipments already in place. There was space in the main electrical cab, cooling water available, and even some space in the control room, okay, to be used. So the condition to install the balance of the plant, so everything that is around the single equipment, was really better. So we have the same power cycle, the same equipment, same size, same manufacturer, everything is the same, apart from the, let's say, characteristics of the plant that I showed you just a few minutes ago. So, less distance and in general, a better condition of the plant itself. What does this imply? Okay, I cannot give you real numbers, but just to give you the impact on CapEx, so on the cost of installation of the plant, the second example had a 30% less of impact in the project, just due to the fact that you can see the distance between the waste heat recovery unit and the plant auxiliaries is less, and the fact that we have firefighting availability and control room space availability. All the rest of the data are identical. Okay, same, as I said, same equipment, same anything, but just these three single topics change 30% the impact on CapEx. So just to get to the conclusion also, because I don't have, we could discuss about this hours, okay? Anyway, just to take some technical conclusions, the main fact is that there are issues related to the balance of the plant, and potential tips can allow a project to go on or not. Other than the one that I already shown, that are, the connection to the grid, means if you have, and the use that you want to do about the generated power has an impact on cost. Is there the needs to have inventory? What is the status of the electrical grid around the plant? Okay, is it old? Can this grid sustain the additional generated power of our waste heat recovery unit, power cycle? What is the safety, environmental constraints inside the plant? You saw we went to a cement plant. In the cement plant, there is no, let's say, skilled personnel that is capable to host and to manage high pressure pipes. I came from the oil and gas, and for us, high pressure CO2 is a very easy business. We are used to super high pressure gases, like gases or high temperature oil. So CO2 for us is a very easy gas. Anyhow, if you go to a cement plant, they are not used to this. They don't have any procedure. They don't know where to cross the pipes, how to deal with it. And this is a cost for the final customer. Then if you go to a brownfield, having a good plan to make the installation, to minimize the plant shutdown is a must. You are adding something to an existing plant. You cannot stop the plant just for months and months, putting out of production the main line of a cement plant just to install a waste heat recovery unit. you need to look at access and logistics. Okay, these are all elements strictly connected to the balance of the plant and system integration, and all of them has a real big impact on cost, even higher than the one before I showed you before. So just as I said, to get to the conclusion, my advices is if you have to install a power cycle using supercritical CO2 in a brownfield plant, you have to prepare a checklist, not only to, let's say, examine the plant in which you have to place your cycle, but also to have a better idea on how to discuss and cooperate with the customer to gain the most from existing structure, because it is clear that the most you can mitigate of the cost and technical problems generated by installing your plant, by the system integration and balance of the plant inside the client plant, the most easy will be to make your project going. Maximize modularization and footprint flexibility means if you use modular solution, as we did in our project, it will be easy to have easier installation, to have a lot of pre-testing, and so minimize also the plant shutdown during the installation of the cycle. And also you have a lot of flexibility to install the plant, the better it is inside the existing brownfield. The most you can keep everything close by. This is seems obvious, but it's even the impact is even higher than what expected. It's not only a matter of additional piping you have to lay down. It's a matter of also of keeping the temperature up, and it's a matter of having the good, let's say, reactions in the cycle itself, and so keeping things at the lower level. And last, also, you have to look beyond the fence of the plant, and if you want to make a good system integration and a viability, good balance of the plant, you have to look around, having good road access and electrical grid and so on. And I think this has to be done even before selecting a site, even before starting discussing with the customer, in order to, as I said at point 2, cooperate with the customer to give him the best solution he can have. That's it. I don't know if I get to the end of my 15 minutes. I guess so. And obviously, I'm fully open to any question, discussion that can come out from my presentation.
Excellent. Thank you very much, Matteo. I guess your enthusiasm and in-depth knowledge on this subject is quite evident. So I wrote in the Q&As that this is where you can write your questions for the time being. If you wish, you can keep them for the end. For the Q&A session, you can ask orally. So it's entirely up to you. So now it's up to the second speaker to take the stage. While he's getting ready, I'm happy to present you Raymond Decorvet, who has a degree in economics. His expertise is business development, sales, and marketing. He spent 25 years in information and communication technology in various companies in different management positions. Since 2018, he works for MAN Energy Solutions Switzerland in global business development for large-scale heat pumps and thermal electricity storage. So Raymond, over to you.
Yeah, thank you very much, Jitka, for this nice introduction. And hi, everyone. Good morning, good afternoon. It's a pleasure to be here to introduce you to large-scale supercritical CO2 heat pumps. And I have to admit, I had to Google, or someone had to tell me, what is balance of plant? What does that mean? But going back in the 90s, when I come from computer science, I remember there was a company called Digital. Maybe some of you still remember that great computer company. They made everybody in the market crazy because they came up with an extremely great processor, the fastest processing processor. And everybody was afraid of that. When it came out, it was not the case that we had to be afraid of. The point was they had the fastest compressor built in their computer, but they didn't work enough on the bus system. So it was processing the data the fastest, but didn't get out the data out of the system. So the overall performance of the system was not accurate. And I think this is also what's happening with the plant. You have to consider all the auxiliaries and all the parts which are in such a plant. We just heard from Matteo. I heard a lot of things in the Slido, which what I can cover is Carnot battery, heat pump, waste heat recovery, turbo machinery, refrigeration, system integration, heat exchanger, cooling, compressors, and efficiency. So let me start. I hope you can see. Okay, 2 slides about MAN Energy Solutions.
We don't see your screen, Raymond.
You cannot?
No.
Oh, hold on a second. Here we go.
Yes, it's coming. Oh, excellent.
Yeah, 2 slides about the company. We are an international company, about 14,000 employees. And as you can see, we have a lot of factories in Europe. And we are headquartered in Germany, in Augsburg, near Munich. Besides some other markets, we are now having a strong focus on large-scale heat pumps, carbon capture, and hydrogen. And these new markets are also covered by our international service organization, PrimeServe. I think we should not forget this. We have to come up with technology to fight climate change and global warming, and a good way is reducing CO2 and to decarbonize heat and cold production. What are the best ways forward? It's first, certainly, we have to reduce energy consumption as a whole. We have to increase energy efficiency with the technology we bring to the markets. Sector coupling, and we have to invest in proven and mature technology which we have on hand right now, which is renewables, heat pumps, and also large energy storages called long duration energy storages. And this is what I'm talking about today. So heat pump technology is becoming more and more relevant for the power sector. Why? It's not only decarbonizing the heat and cold, but also we can fight the energy crisis, the looming energy crisis. Why? If we integrate renewables, then heat pumps is possibly, and it's not possibly, it is the most efficient technology to use for the usage of electricity and to turn it into heat or cold. It's proven, it is reliable, and it, as I see here, as you can see here, has a high COP if we want to. We also can build large thermal storage with heat pumps to make best usage out of renewables instead of to curtail them and also to balance the fluctuation. Grid balancing is also what we can do with large-scale heat pumps. So we see in a lot of countries where we have huge amount of renewables that we have great fluctuations. We can do that. I come to that in a second. And also sector coupling, exploiting synergies among different business sectors. And last but not least, we can build with large-scale heat pumps. We can build electricity storage, and this is called MAN ETES, electrothermal electricity storage, which is basically actually a Carnot battery. So when we see this, again, if we have here in the middle a heat pump delivers heat and cold. So maybe here on the city municipality, we service a district heating network, and typically they are not using the cold, which is a shame. But maybe the cold can go to a data center for cooling. On the other hand, the data center actually providing waste heat, this can be recovered to run the heat pump and using the waste heat from the data center as a heat source for the heat pump. This also, of course, goes along with the industry. And with the heat pump, as I already said, we can integrate renewables and we can help the TSOs and the DSOs to stabilize the grid. More than 50%, or currently 50% of all the energy used on this planet is used for any type of heating or producing heat and cold. And cold is the new heat. More and more demand for cold we see in the projects which we got in our pipeline. What we also have to know, with heat pumps, we can provide, of course, hot water, cold water, but we also can produce steam. And importantly to know, most of the processes in food and beverage, in heat, district heating, in other processes we see in industries are actually below 200 degrees. So with heat pumps, we comfortably can serve these kind of processes. Now, talking about the CO2 heat pump. So we can supply heat, cold, thermal storage, but also electricity storage. We integrate renewables and we highly decarbonize, of course. We use CO2 as a refrigerant in our heat pump. And if it comes to thermal storage, we just use water as the storage medium. That makes our solution extremely sustainable. It is scalable and flexible, and we only use proven off-the-shelf technology. What capacities are we talking about? We are talking about up to 50 megawatt of thermal heat and thermal cold, 30 megawatt of thermal cold, which we can produce with one single heat pump. If it comes to electricity storage, then we can store up to 200 megawatt hours a day. The temperature levels we can provide with our heat pumps is up to 150 degrees. It could be higher. And the COPs we are achieving, combined heat and cold, is 5 up to 7, depending on a couple of parameters. The good thing is, if we use our technology for storing electricity, there will be no degradation during the lifetime as we talk normal physical processes, no chemics. So this is how the process works. It's as what you can see here, a normal heat pump loop. We start here with the CO2, which is fluid, which is cold. Here is our industrial compressor, a turbo compressor, and we compress the CO2 up to 130-40 bar. And here in this stage, we are already in the supercritical stage. Now we bring the CO2, which we can bring up to 190 degrees and more, to this heat exchanger here, where we now can supply the district heating with heat, or we can actually build hot storage either with one or several tanks. When the CO2 is leaving this heat exchanger here we have an expander, and now we can produce either cold water or even ice. And then the CO2 flows back and the circle goes again. Nothing really special, honestly, only maybe the CO2 and the capacity. And now have a look to the next slide, to the inner cycle. I hope now you can see it has changed. And now this is the discharging cycle where we can produce electricity out of the formerly stored heat and cold. I start here on the cold side again with the CO2. The CO2 is now liquid on the low pressure. Now with this liquid pump, we bring the pressure to again about 120, 130 bar. With the same heat exchanger as before, we add the formerly stored heat from these tanks to the CO2, and here it becomes supercritical again. And in this stage, we bring the CO2 over a turbine, and there is a generator attached, and this is how we re-reproduce electricity coming out of the iced and formerly stored heat. The round-trip efficiency is about 50% today, but we can increase, we believe that we can increase that to 60% over time. Now again, what you can see, we have a very simple heat pump here on the right side. We have the same heat pump with thermal storage, or we have here the ETS system with the capability of the re-electrification. And I'm sure you now have a lot of ideas what this application could be used for in district heating, cooling, large hospital, airports, university campus, you name it. To tell you about the capacity of our solution, what do you think? How long does it take to get this Olympic basin with 2.5 million liters to the boiling point? I make it short for you. With just one single unit, it takes less than 4 hours. Or we could freeze the whole thing in about 11 hours. So these are the magnitude of capacity we are talking about with our large-scale heat pump. And here is one. Here we see the turbo compressor. We come to that in a second. Here we have the large evaporators. Here we have the heat exchanger to the hot side of the heat pump. We have 3 different sizes of this compressor. And as I already mentioned, we can provide up to 50 megawatt of thermal heat and 30 megawatt of cold at the same time at high temperature levels. We use any kind of liquid water as a heat source. It can be also geothermal, but it also can be ambient air and, of course, industry waste heat. Coming to the compressor. A typical ordinary compressor, which we also have in our portfolio, is typically using a motor, a gearbox, and then the compressor itself. The compressor I'm talking about has about a third of the size. It has a compressor and an integrated motor. As you already can see, it has a reduced footprint, and it has an integrated high-speed motor. It has no gearbox, and it runs on magnetic bearings, and that's why we don't need any lube oil to run it. It is hermetically sealed. That means no leakage and no loss of refrigerant. And here it is. Here we see the integrated motor again, and here is the compressor. The CO2 which is going through this compressor is actually cooling the motor. And again, no lube oil, because we have here magnetic bearings. And what you also can see here, hopefully, the compressor is completely sealed. It is a barrel compressor, which means if we open here on this side, we can pull out the compressor and bring in another one which maybe has been refurbished, and then we can close the case again. And here we go again with running the compressor. You remember the expander. We have integrated now the expander on the same shaft like the compressor. So when the CO2 on the high pressure is coming and hitting the expander, it helps to run the motor and the compressor. And this is giving us up to 10 to 15% of power savings again. Now I come to something very interesting. Thanks to the magnetic bearings and there is no lube oil in our compressor, we can ramp up the compressor by many, many megawatts within seconds. And this is important. If we have the grid, then the grid has fluctuations, and these fluctuations sometimes have to balance within 30 seconds, and then we have some other areas where it takes a little bit more time to get the grid balanced. What we can do now is we can run the system at 8 megawatt, even though it has a nominal of 16 megawatts. So we have 8 megawatt where we can play with. So when we run it on 12 megawatt, we can increase now the load of the system by 4 megawatt or lower the part load of the system by 4 megawatt within 30 seconds. And this gives us the ability actually to run and provide grid stabilization in the primary reserve as well in the secondary reserve. And this is also interesting if you operate a compressor or a heat pump like this, because it is really value a lot of money because the TSOs are more and more asking for this capability. When it comes to robustness of our solution, 2 of these compressors are running since September 2015, 300 meters below sea level in the North Sea. It is not a heat pump, it is subsea compression application, but as you can imagine, there is no chance to make any maintenance since September 2015, and they run down there with 100% reliability. Now I come to a project in Esbjerg. This is our first large-scale heat pump project using the CO2 heat pump. So this coal CHP is going to replace with a bunch of other heat sources for the district heating network. Our CO2 heat pump actually saves up to 100,000 tons of CO2 a year, which is the equivalent of about 55,000 cars. And we will go operational in about 2 or 3 months from now. And this is how the site looks like. Here we see the building with the 2 heat pumps. Here we have a large thermal storage, and here we have a wood chip boilers, and here some other technologies for backup reasons. What we are using now is 2 of these heat pumps to provide 50 megawatt to the district heating network. And we are using seawater in wintertime with a temperature at 1 degree. And because it is salinated, we can actually still take out 2 Kelvin and bring it 1 degree back to the sea. And if you now see the COPs in wintertime using 1 degree of seawater as a heat source, I think this is really phenomenal to have such a high COP, and in summertime, of course, it goes up. This is, and we provide in one stage a lift from 1 degree to 70 to 90 degrees, what is the forward temperature demand. And here again, the other technologies for most of the time backup reasons. And here are some pictures of the site. As you can see, this is real. And this is also real. Because of the large amount we need of cold water from the sea, the evaporator has a huge size, of course. So we bring through this evaporator up to 5,000 liters of seawater every second, where we take out about 2 Kelvin. Here's some more impressions about the facility. So these are all the pictures, but you can now see a lot better these large evaporators. Here is our Hoffing compressor. and a lot of piping, as you can see here. And here is the inlet pipes. They have a diameter of 1.2 meters to bring these 5,000 liters a second to our heat pumps. And here it is in the building. Some more pictures. And this is how it looks like. And I hope it already looks even cleaner because we go soon in operation. And if you find this already impressing, we now last year won our second project, very similar. So we also are replacing this coal CHP with heat pumps, but this time we are using 3 seawater CO2 heat pumps, and we already delivered 134 megawatt of thermal output, which means 44 megawatt per heat pump, which is more than in Esbjerg, as you remember. The electrical input for each compressor will be more than 14 megawatt. The scope of supply, which we typically deliver, is this: the compressor unit and everything what it needs between the evaporator and the heat exchanger to the heating network. But if you really want us also to build your building or bring some streets to the building or whatever, we can even support you on that. And this is my last slide. Remember what I said, heat pumps are more than just a device for heating and cooling. They can serve the energy system. Thank you very much.
Thank you, Raymond, for a very informative and engaging presentation that you have just delivered. I enjoyed listening. Thank you so much. So there is a third speaker waiting and getting ready for his presentation. And I have the pleasure to introduce you Xijia Lu, that has served as NET Power's Chief Innovation Officer since January 2024. Prior to joining NET Power, he worked for 8 years for 8 Rivers Capital, leading the research and development of the solid fuel-based LM cycle technology, which is a direct-fired supercritical CO2 cycle. Xijia received his PhD degree in mechanical engineering from the University of New Orleans, and he has over 30 publications and over 100 patent filings. So, Xijia, the floor is yours.
Okay, thank you so much.
If you can share your screen.
Can you hear me?
Yes, we hear you, but we don't see your screen yet.
Okay, let me share the screen. Give me 1 second. Can everyone see my screen now?
Yes, we only need the presentations mode. Yes, excellent. Now we have it. Perfect.
Oh, perfect. All right. Thank you so much, Jitka. Hi, everyone. Good morning, good afternoon, good evening, depends on where you are. So it's my honor to present today to give everybody a quick overview about the power technology, which is direct fire oxy fire SU2 cycle. So a quick overview, who we are and what we do. So NET Power is a US-based clean energy technology company that has developed a gas-based power plant that generates clean power with zero emission, near zero emission. So we employ the oxy fuel combustion and utilize supercritical CO2 as the turbine working fluid to efficiently produce the clean and low-cost power while deliver a pure stream of CO2. The cycle capture the CO2 inherently, the CO2 for sequestration and utilization. We have started this program, NET Power technology, about decades ago. So we have developed our demonstration plant, which is 50 megawatt thermal input demonstration plant down in La Porte, Texas, was commissioning in 2018 and has achieved over 1,500 hours of the operation able to synchronize to the text grid in 2021. Right now, actually, NET Power announced agreement with Baker Hughes to design and manufacture the key plant equipment. I expect delivery in 2026 and 2027. Several projects in various stages of development for the first utility scale plant expected online in 2027 and 2028 timeframe. NET Power went public in June 2023, and successful energy entrepreneur Danny Rice became NET Power CEO. Our strategic partner and shareholders, including Occidental Petroleum, Baker Hughes, Constellation, and SK. The right-hand corner shows the 50 megawatt demonstration plant down in LaPorte, Texas. So let's get a little bit details into the cycle. So NET Power, it is the oxy-fuel supercritical CO2 cycle, really try to decarbonize the power sector using natural gas as the feedstock. So this cartoon figure shows 10,000 feet overview of the cycle. So the combustor received the natural gas and oxygen from air separation unit for oxy combustion. The combustor operate at close to 300 bar and 1,000 degrees Celsius. The combustor flue gas pushed a turbine for power generation, and turbine exhaust gas still had very high temperature, close to 600 C, and we send the flue gas into a heat exchanger for the heat recuperation. After this heat recuperation, the turbine exhaust gas being cooled down to near ambient temperature. At this stage, the liquid water being knocked out from the gaseous CO2. So CO2 is pretty much at pure, 100% purity. The low pressure CO2 will be recompressed and repumped to very high pressure to maintain the mass balance of the plant, how much natural gas and how much oxygen gas get into the system, how much water and CO2 coming out. So a small portion of CO2 will be exported to high pressure to pipeline. The majority of the high pressure CO2 at 300 bar will be preheated to very high temperature. So this heat exchanger really transfers the heat from turbine exhaust back into the recycled CO2, then recycled CO2 back into the combustor to serve as the temperature moderator, because the flame temperature of the oxy combustion is above 2000 C. So the majority of the recycled CO2 will be re-injected into the combustor to control the turbine inlet temperature. So this is a very quick overview of the cycle. The key target statistic for the commercial unit, it is about 50 million scf per day natural gas coming in, generate about 250 megawatt electricity as the net output. The CO2 export is roughly 850,000 tons per year. This slide really shows the LaPorte demonstration plant. We built it up in LaPorte, Texas. The cooling tower, water separator, combustion turbine, heat exchanger, turbo expander generator, all the BOPs. So this is the 50 megawatt thermal industrial scale demonstration plant, only 5-acre footprint, very, very small. Start commission in March 2018. So total runtime is roughly over 1,500 hours. So during the 3 test campaign, we're able to test all BOP, all key equipment sit in cycle, including compressor, pump, combustor and turbine, heat exchanger, and balance plant. We're able to test our control systems. The facility exceeded 925 degrees Celsius design temperature and 300 bar pressure. And we're able to sync the turbine power to the grid. As we're moving towards to the commercial stage of the technology, in 2022, we started to joint development with Baker Hughes, established a strategic partner with Baker Hughes, really ramping up the commercial phase of the technology. So we're able to leverage turbo expander architecture leveraged decades of Baker Hughes experience across its technology portfolio and installed fleet. So Baker Hughes come on board really helps us to drive us the technology to the next phase. Baker Hughes is going to supply the key equipment, including turbo expander, combustor, all the key pumps and compressors, additional BOP, as well as the equipment service agreement. So currently, the demonstration facility is being upgraded and modified for Baker Hughes test campaign. So the preparation activities include relocation of the recycle compressors, piping instrumentation enhancement, upgrade to the distributed control systems. The test campaign plan, we're gonna start to test the combustor components this year. Demonstration and utility scale combustor can testing in 2025 and demonstration turbo expander testing expected in 2026. There's a concurrent product development and demonstration programs really accelerate commercialization of this technology. So we're working on the process and equipment development along with Baker Hughes for the cycle optimization, utility scale plant design, and Baker Hughes equipment and validation. And then we move into the demonstration phase. We're going to use our La Porte, Texas facility to test the key combustor component turbo expander for Baker Hughes and also for the control refinement. In the meantime, we already start the FEED study for our first commercial plant down in Texas. So the FEED study kicked off last year and expected to complete it later this year. We're working with Zachry Group for the detailed design, and the first commercial scale utility is started commissioning in 2027 to 2028. This slide really shows all the key BOP and key equipment sit in cycle, and this is the power supply chain strategy to support ramp up in the deployment. So the strategy we have is really we want to work with all world-class equipment suppliers as well as the EPC partners to standardize our design of the plant as well as the key piece of equipment sitting in the cycles. We have announced partnership with Baker Hughes on the turbo expander as well as the compressor pumps, turbo machinery in the cycle. We also announced partner with Lummus for our heat exchanger design and supply. Zachry is working with us on our FEED study of the first utility scale commercial plant, and they're going to be the first commercial plant EPC partner. Through the EPC and FEED study, we're able to standardize our design across the multiple EPCs, so we're able to license our technology around the world in the future. In the meantime, we follow the same strategy to work with world-class air separation unit partners, the partners for the balance plan and modularization. This is the first commercial project we announced as the Project Permian, the first utility scale net power plant, and net power will be the plant developer and project developer. So our goal is we try to develop our first plant to demonstrate the clean, reliable, and safety commercial plant operation before we can hand over to our partners, utility partners, to build multiple plants in the future. So the background of Project Permian, it is 250 megawatt scale electricity plant. It's located near Midland, Odessa, Texas, with existing gas and power and CO2 infrastructure. The FEED work with Zachry commenced in Q1 2023 and expected to conclude in the second half of this year. We already submitted interconnection application in ERCOT, and also all captured CO2 will be tied into the Oxy's extensive CO2 network in West Texas. So the right-hand side then show where's the location of the plant in West Texas. So we're starting the FEED study, and the commercial operation is targeted in second half of 2027 and first half 2028. The supported investor and strategic partner include Occidental Petroleum, Constellation, SK, Baker Hughes, Lummus, and Zachry. With that, to sum up, the Empower really delivers an energy trifecta. So we're able to provide clean, affordable, and reliable electricity from natural gas fossil fuel. That's all my presentation. I'm open for all the questions from the audience. Thanks so much, Jitka.
Thank you very much, Xijia, for your presentation. Your ability to present complex concept in clear manners. It's truly impressive. Thank you very much.
Thank you.
So now we are left with the last, but definitely not the least speaker. So the last one, number 4, is Joshua Warren, who is a senior research engineer at Southwest Research Institute in San Antonio in Texas. Joshua has been dedicated to the STEP demo project and sCO2 research since he joined his company in 2020. He has led the installation and commissioning of the inventory management system and the main compressor system for the project. He has also consulted for several other small projects involving sCO2 cycles during his time at Southwest Research Institute. So over to you, Josh. Well, I see that you share your screen. We see it very well. So off we go.
All right. Well, thank you for that brief introduction, Jitka. And thank you for inviting me as part of Southwest Research to be part of this webinar. So I bring a little bit different perspective. We are not a commercial company, but we are a applied research and development company. So Southwest Research is actually funded in 1947 in San Antonio, Texas. There's a general aerial view of our large campus that's there. We are a 501c3 nonprofit, so we have internal research opportunities that we actually fund and can do exploratory research just from internal. We've got many industry and government contracts. I believe that is the 2022 numbers is 726 million in annual revenue. We have almost 3,000 employees now. We have come up and down a little bit with COVID the past few years, but are settling in and have been expanding the past few years again. Again, our campus is over 1,500 acres in Texas. It's was fairly cheap land at the time, but it's getting more and more expensive as land is everywhere. But we've got a lot of useful space and a lot of labs that are available. The real thing that is advantageous about Southwest Research is we have a bunch of different divisions that cover many industries and many technical aspects. So what you can see there is our tagline or our motto there is where we can do anything deep sea, deep space, and everything in between. So we've got a subsea testing group that actually helped develop the Alvin pressure hull for one of the deep sea submarines. And we've also got space science and engineering groups that help develop probes and satellites that go out into space. That little circle that's on our campus, that is the STEP facility, which is kind of what we'll get into a little bit more detail now. So the main project I want to talk about, which is my main focus, is our STEP demo project using the supercritical CO2 recompression closed Brayton cycle. So the STEP demo project is funded by the Department of Energy and National Energy Technology Labs. We are led by GTI Energy, when we are one of the main partners along with GE Global Research. Our goal is to build a 10 megawatt electric sCO2 pilot plant. And our total budget has increased a little bit more, but the last number I have recorded is 156 million. It includes, I think, 20% cost share. So government is providing most of the funding, but we do have industry partners that are working with us as well. So the roles that SwRI has in this project is we are the host site. So we built this brand new facility from a greenfield, and we got occupancy in 2020 and have completed installation at this point. But we are the focus of system integration and the operation of the plant, including the data acquisition and controls of all the equipment. We performed all the piping installation, and we actually have some more piping to do for our phase 3 implementation for the actual recompression part of the cycle. We are also responsible for the inventory management system, which is what I'll get into more detail here in a few moments. We helped design the turbine, so we own the mechanical design. GE assisted with the aeromechanical design for the actual blade pass. And then we also led the development of the heater protection valve, which allows us to vent CO2 at up to 720 C while we're operating if we need to. So we have already started. We've been operating our main compressor loop for about a year now. We've finished installing our turbine side of our simple cycle loop in October of 2023, and we are currently in the commissioning phase. So the step demo site is the building that you can see there on the right-hand side of the slide. And then the smaller shot there is actually our turbine train with the bypass compressor skid actually ready for operation, but not piped in yet. So the recompression closed Brayton cycle is the specific sCO2 cycle that we're trying to use in the STEP demo project. It has a high performance. Our goal is to prove efficiency up beyond 50%, depending on how the cycle is actually partnered. The goal is to get the turbine inlet temperatures up to 715 C. For our simple cycle configuration that we're operating now, we'll get up to 500. We have 2 parallel compressors with different head curves because one of them operates at near the dome for the supercritical point. And then the bypass compressor is our recompressor that still keeps our hot gas and just recompresses that. We have multiple heat exchangers, so we have 2 stages of recuperation. We have a high temperature and a low temperature, and then we also have several water cooling systems around the plants that help us reject the heat. One of our main goals is to measure the system and component performance. So this facility that is on our campus here in San Antonio will be a test bed in the future for as we make changes to components and move forward in future designs. So we've got 6 main ways to actually control the cycle. So 1 is our heat input. 2 is our heat output. So you have a Q in and Q out. Those are typical of any cycle. Number 3 is our inventory, which is actually what we'll get into more detail. It's managing our mass of CO2 in the system. 4 is a turbine throttle valve, so we can actually use that to change our load as well. And then we can actually change our operating points around the cycle as well using our main compressor IGBs and our bypass compressor IGBs. This gives us an enormous amount of flexibility to try and go operate at different speeds with different efficiencies. But the end goal is to prove that the RCVC cycle can actually get beyond the 50% thermal efficiency. So the inventory management system is what we will focus on here. So again, taking a step back, from balance of plant perspective, there's a lot of things that I consider balance of plant, and it's really just the ancillaries that make up a plant. So that's your cooling water system, your lube oil systems, your instrument air. anything that is not your compressor, your turbine, your critical components of the cycle. So there's a lot of those that are universally applicable. So magnetic bearings or lube oil bearings and cooling water systems, those are universally applicable to a lot of different cycles. But specifically for supercritical CO2, an inventory management system and just a closed cycle becomes important. It really controls the amount of CO2 in the system, which then affects the system load. And with the shift in decarbonizing the world, having the inventory management system helps control any lost CO2 and actually minimizes any leakage, allows us to transfer that mass in and out of the system at will without having to recapture or have some other carbon offsetting technology to minimize our carbon footprint. So it is responsible also for the initial fill of the system. And it supports the auxiliary systems, in our case, including our dry gas seal systems. And again, it can enable fast transitions between load points, but your design of your inventory system is critical there. One of the things I wanted to point out especially is load. So I noted that we can control our load using our turbine control valve, but we can also control it using inventory. So I've highlighted two cases from the STEP cycle, which is our case 154, which is our 40% load case at full temperature. We actually use inventory control on case 154, and we can achieve, or we expect to achieve, about a 37% efficiency for the entire cycle. If you do that same case, so you're at 40% load, but you're only using the turbine throttle valve, that efficiency drops down to below 30%. So it really shows how inventory control can be a huge key for increasing the efficiency of your plant versus just having a throttle. The throttle is still helpful because it can help you make those rapid load changes as needed, but the inventory control is really what you want to use in the long term to increase your cycle efficiency. So the inventory management system that we have, so this is an earlier design, but the only thing that's really changed from our perspective is for cost reasons and a few other reasons, we've removed the cooler that's there at the top of the slide. But there are a few main functions of an IMS, and for us that is the liquid supply in our fill system, and then we manage our inventory control, and then also our dry gas seal supplies as our third critical item. Depending on your plant configuration, you can also get other auxiliary supplies, but we do not have any main drivers for that in our plants. So looking at the liquid storage and fill system, so we're looking, our system has a bulk liquid tank and coupled with a system of cryogenic pumps, and then a large vaporizer that feeds it into the process. So our fill system is comprised of a 30-ton liquid storage tank. This allows us to operate for about a week at a time in our simple cycle configuration without needing to get more CO2 delivered to site. That helps us manage leakage in our initial fill. We have a dual redundant liquid pump system, and the sizing is needed to match the vaporizer duty. We also have VFDs so that we can meet our required outlet temperatures for the process supplies. But the real goal of this system is to take the dense liquid storage and actually vaporize it to greater than 40 C as we pump it into the building for our use in the demo facility. And the major note that I want to note on the fill system side of the IMS is the sizing of your fill system is a critical input for depressurized startup times. If you have a commercial plant that's like on the order of 50 megawatts, then you could be filling for days if you're running at similar flow rates to what we have. We can fill our plants in the course of about 3 to 4 hours for our 10 megawatt plant, but yeah, your inventory, your fill system sizing is critical for getting your depressurized startup times. Moving into inventory storage and control. So we actually take from our compressor discharge at the top right, we regulate that pressure to make sure we don't overpressurize anything. You can have an optional cooler to actually control the temperature depending on what your compressor discharge is. We've decided for our project, for cost and other reasons, that that cooler was not needed, so it has been removed. Then we have a control valve that allows us to pump that compressor discharge into our inventory storage tank. And then we have another control valve that's not shown here as it goes back to compressor suction. So the inventory control system really allows movement of the CO2 from the process to the storage tanks and back. There's a couple of ways that you can do this, and the major way that we do it is the natural pressure differential. So we actually, if you look at the charts on the lower left, you can see if we're operating at 100% in case 151 on the right side of the graph, our compressor discharge is about 265 bar, and our suction pressure is going to be on the order of 85. So that large pressure differential will actually drive the flow. So we open our withdrawal valve from the compressor loop, and we're actually pulling that high pressure off of the compressor discharge and storage tank pressures. So we will slowly transition from 100% back down to 40%. As we pull the high pressure discharge off the compressor, we slowly increase our pressure so where they're very close between the compressor discharge and our inventory storage tank. And that also lowers our compressor suction pressure as we pull inventory out of the system. Another option that you could use for the effect is a pumping system or just a small compressor that could actually drive the flow and remove that from the loop. But the other point that I want to make is temperature of the storage tanks has a significant effect on your capacity. So your density of CO2 is very drastic when you're around the critical point, that's 31 C. So at high pressure and high temperature, so looking around your compressor discharge, so at 100% load, your density is the blue line there on the right graph. You're at higher pressure, so but also higher temperatures. So as you go up in temperature, your density comes down, and you've got a large difference in density between how we operate at 100% load and at 40% load. And that can actually change how much tank volume you need for your inventory storage system. So that density change actually becomes very critical, and also becomes critical for the selected temperatures for your storage tanks. So in our choice here, we've tried to minimize the required storage volume. So we are actually planning to operate our IMS tanks around 50 to 60 C. So that's kind of where the gray line hits a minimum. But that gives a volume. The gray line is basically a projection for removing 1,500 kilograms to go from 100% load down to 40% load, and how much volume we would need to be able to store that volume. Then the third and other critical component of this is the dry gas seal supply. So under normal circumstances, you would flow from the compressor discharge and just go bypass the inventory storage tanks, and then you would actually go through bypass our dry gas seal booster system, and then we have a buffer tank or a rundown tank, and then you'd supply that to your dry gas seal systems. So dry gas seals need higher pressure than your suction pressure, your low side pressure in the loop, to actually drive the flow through the dry gas seal and help contain the process gas within the system. So during operation, this segment is passive, and compressor discharge will just bypass our dry gas seal supply system. The buffer tank will act as an accumulator or rundown tank during transients and also during the shutdown process. This gives us on the order of 15 minutes to half an hour of not requiring any changes. We can just let the buffer tank operate to provide that dry gas seal flow. But whenever we are during shutdown for pressurized holds, we are a research firm with a fairly small team, so we end up needing to shut down overnight because we don't have 2 shifts. We're working on getting that set up so we can do our long-term testing. But the boost pumps actually provide that pressure increase and drive the flow during pressurized holds. So again, if you don't have an IMS system, then you're going to be filling from your liquid tank and venting off any excess CO2 whenever you're trying to transition from load if you want your cycle to be efficient. So the boost pump is another arm of the IMS system that will actually minimize the leakage by just continuing to recycle the flow from the process loop back in through the dry gas seal system, and then from there it goes through our supply piping and back to the IMS. So with that, that covers really the major aspects of our inventory management system. So again, Southwest Research is a research firm. We do a lot of different things, and feel free to ask any questions.
Thank you very much, Josh, for your presentation, for your insight and expertise. I'm sure that this was a very valuable presentation for the audience. So this is it, 4 presentations for 4 great speakers. So now it's the time for the panel session. So I will give the floor to Marco, who will manage this this part of the session.
Yeah, thanks, Jitka. This has been very, very interesting. We've seen a mix of insights on components that are part of the overall plant, which are usually overlooked, and tips and hints on how to minimize the cost, so to maximize the financial viability of installations, but also applications that are non-conventional. I mean, in the past, when we addressed the previous episodes in this webinar series, probably we almost implied that what we were talking about was the indirect fired CO2 cycle, but we didn't specify for which application as well. So then also this is, I believe, something important to keep in mind, that as in theory, as technology goes, it is very flexible, and it can be used in a number of different scenarios. And again, we need to remember that it is still, I mean, part of it, it's still to be considered in its infancy. As we have heard, a lot of the things that are happening are still in the mid-tier range, so in between 5 and 7. So that means that we haven't got, for a number of the components, an established supply chain. And yeah, I was really, impressed by the effort that Xijia has shown us of establishing early, a supply chain in order to be able to secure prices and make sure that you can deliver at a certain cost. That I believe this is very important. And as Matteo said, is one of the reasons. Now, cost is one of the reasons that some other project suffered. So I see there is a question for Xijia on the Q&A. So maybe I'll start somewhere else. So maybe you can, if you want, you can type your answer there, and maybe I can start with our last panelist. So last presenter, Joshua. You said yourself, the STEP project is coming into maturity, as the design and the installation has been in progress for some time. Ideally, or initially, as much as I remember, the target application was to be CSP with a target inlet temperature around 700 degrees C. A few years down the line, what can you tell us about that idea? Can you reflect on whether you start to see the application being the real one, or do you see other candidates, and why?
Yeah, so thank you for the question, for starters, and I appreciate you being on the panel to help share the technology aspects of everything. So really, the recompression Brayton cycle is ideally fitted, especially for high temperature. That's where the efficiency really gets up beyond the 40% hopefully into the 50% range. So it really depends on your heat supply. And for most applications, that's where we started with the CSP. But also in power generation, this cycle can be seen as a replacement eventually for the steam cycle. And that's where I kind of expect the first adoption to really occur, because it is a more standardized process. You have a consistent area of waste heat that comes off of the end of a natural gas-fired turbine. It's much more, I guess, base load. It's less variable. So as the sCO2 cycles get more traction and become more understood, I think we will see it get into more applications. But I mean, as you can see from our panelists here, we've got sCO2 being used in a variety of different cycles already. It just depends on the large scale. At least for the closed cycles, though, I think I see it as the first real application for power generation. I expect would be for a replacement for similar to a steam cycle.
Okay, good. Yeah, hopefully we can get the same economy of scale of components that are used in the steam cycles. That's what I guess we all hope for.
Yeah.
So yeah, thanks for the insight. And I see no other questions from the Q&A, so I'll go on and ask about stuff that I've been reflecting on. And yeah, maybe as we keep, or at least I keep going on and hit my head on the cost of the components, yeah, maybe I will ask a next question to Matteo. So during your presentation, you were focused on how you tried and the insights that you get out of minimizing the cost of the balance of plant. Overall, no, what do you think is the impact on the typical, probably waste heat installation, waste heat recovery installation, or if you manage to also look at other type of installations that works as well, and what do you think is the effect on the economic viability of the project of such a cost?
Well, obviously, as also Joshua said, there are a number of applications and a number of sizes. So obviously, the impact of the balance of the plant itself, it depends among the size of the plant you are talking about and the application. So it's, but to be general, I would say that from my experience, it goes from 20% to 25% of the plant. That it seems not so much, but eventually, many projects are driven away just by 10% of difference in cost in respect to an existing technology. In general, what I think is what you said before, just a few minutes before. The fact is that it's not only the balance of the plant; it's the whole cost of the solution of the technology that has to be improved a lot. This is, this is part of the game, as you said, the technology is really in its early stages, and the fact is that it is confronting towards technologies that are already present in the market since tens of years, and where the supply chain, the materials, it's really at its top of maturity, and the costs are so low. Actually, the idea is we have to fight even to get this 25%, the lowest we can get, in order to make the technology going. So as I said, if you look at my presentation, the second option is 30% lower. So you reduce this 25% to 17, 20. It is not enough, but you see, just thinking a little bit more, so making our engineering work better, and can reduce significantly the cost, and so also as you said, the viability of the project. This is the first step we have to do in order to get the first real examples of technology going, and then benefit of the real cost driven that it's the maturity of the market. This is my idea. Thank you for the question, by the way.
You're welcome. Thanks, Matteo. Yes, but I see more questions coming in on the Q&A panel. I'll first go quickly over another question for each panelist, and then we'll go through the list of questions in there. Hopefully that will work for the audience as well. I was particular about trying to get a direct fired application into the webinar, because as I said, mostly we've been talking about indirect fired or indirect heated type of applications, and but that's not what all SCO2 is all about. So I would ask Xijia to just help us reflect a little bit on which are the conditions that will be there so that the direct fire technology can flourish and take a hold on its share of the market.
Okay, thank you, Marco, for the question. I think the direct fire SCO2 cycle really focus on the carbon capture, decarbonize the energy sector from fossil fuel. So we have the different application and niche market, and everybody knows that when you develop the new technology, you will have a higher entry cost, especially in the carbon capture world. So I think which condition we should meet to flourish this market. Number one is for early stage development, the government support. For instance, in the United States, 45Q really played a key role for the early stage project development for the carbon capture projects, right? So the clean energy commitment from the utility sectors, from industrial sector, from oil and gas players, that really helped a lot. And also we need to build up the supply chain for the technology and going through the very thorough technology development roadmap. Infrastructure is very key and important, because you need to build up the CO2 pipeline so that once you capture the CO2, you're able to transport to sequestration dome, to the EOR facilities. So you really need to pour space for the CO2 end use. So I think there's a lot of pieces really to be integrated into a complete carbon capture, sequestration, and utilization solutions. That is something come in my mind. So, Marco.
Yeah, thanks. Yeah, I think one of the points that you mentioned, the infrastructure. Also during your presentation, the leveraging the Oxy CO2 transport network is probably one of the key aspects, not only for the Oxy combustion type of technology, but also in general for carbon capture, to be able to support existing natural gas-fired plants in order not to be able to produce, to be able to continue producing electricity and power with a lower or non-existent CO2 footprint. I think that is very important as well. My last question would be for Raymond. I'm part of the strategic energy roadmap, so the set 6, which is heat and cooling of the European Commission. And one of the focus of that particular integrated working group is also looking at introducing, let's say, heat upgrading and trigeneration. So heat pumps are very important to that particular roadmap in the European Commission scenario. So you mentioned the heat can be delivered up to, if I remember correctly, the number you had on the slides, 150 C. That's what you can usually do. So I was just trying reflecting whether you are looking at also higher technology, higher temperatures for industrial applications, and what do you think would be the space for that?
Well, what I said, what we see most applications, industry processes have a demand of temperature levels below 200 degrees. Of course, there are some, they are really demanding then in the hundreds of grades, but typically in food and beverage, for instance, district heating, petrochemical, for instance, chemical, but also pulp and paper. These are the markets we have focus on. So they are demanding temperature levels, hot water and steam below 200 degrees. And this is what actually heat pumps today already can deliver. Not in all the capacities yet, but we are coming there. And so the EU Commission is very much in favor of heat pumps, of course, because a lot of electrification is going on, and we have to decarbonize the heat and cold production. Did that answer your question?
Yeah, thanks. So let me see if whether there are. Yeah, I see there is one unanswered question. I see you've been typing in the last couple of minutes. So there is one question for Xijia, and I'm reading it out loud. So what's the effect of the impurities in the oxygen and in the methane on the cycle and on CO2 captured? Then it gets technical. Can you give a stoichiometric oxygen to fuel number for the combustion? So I guess that's probably something chemical. What thermal efficiency you were able to achieve in the pilot plant? I mean, if I remember correctly, the pilot plant only has currently only the combustion system installed, right?
Yeah. So okay. So several questions, very technical. First of all, the impurity impact. So the impurity really impact on the parasitic load of the CO2 compressor and pumps, and also CO2 purification units. We do need the CO2 purification unit to meet the pipeline standard, to remove any excess nitrogen or oxygen sitting in the CO2, the impurities, and also from the metallurgy point of view, we don't want like sulfur and natural gas to give you the sulfur corrosion, etc. So I think that's the answer to the first question, the impurity impact. Then the second question is the oxygen to fuel ratio. So previously we did the combustor test down in LaPorte, Texas. We're able to achieve complete combustion with very minimum CO in the combustor flue gas, with a little bit oxygen-rich condition in the combustor. So right now we're working with the Baker Hughes right now to develop the combustor, and we are start the combustor test campaign this year, next year. Really address all the questions you have here. So the previous experience we have is we're able to achieve complete combustion with very low level of CO. So.
Okay, good. Thanks. And then this one, let me read it and see who can be can at best address it. Yeah, I would ask this to Matteo. So the question, I don't know whether you can see it on the Q&A panel, is the one on the top. So at which stage of the cycle and/or plant engineering the balance of plant should be considered? What is your? I mean, you are working on designing planting and modules, so probably your best.
Yeah, exactly. Yes, I was. Thank you for asking me. Yeah, I think that as there are some aspects that for sure needs to be addressed very, very early. I would say in the feasibility area, okay, of the project. So the need of auxiliaries, for example. So you need to know which kind of auxiliaries your plant need and what are the auxiliaries present in the existing plant or whatever in the new plant you have to build up. Then also, I think local regulations can have significant aspects on the balance of the plant. So also this part of the engineering of the balance of the plant should be addressed very, very early in the phases of a project. Obviously, detailed engineering can come later, but as I said, needs of auxiliaries and local regulation should be addressed immediately because they have really impact in the engineering itself of the balance of the plant, in the length of the duration of the schedule, and obviously on the cost, as I said. So.
Yeah, thanks, Matteo. I see another question popped up by Jörg. I believe that this is more relevant to a direct fire type of cycle. So I'd ask Xijia to try and answer. So yeah, the question basically is how do you get the moisture or water out of the CO2? So how's the part of the balance of plant actually structured? And where is it located? I mean, I suppose the dryer or whatever the separator is located in the lower pressure side of the system after cooling. But yeah, that's on top of what I remember about the cycle. You're on mute.
Sorry. To get moisture out of CO2, so combustion-derived water, probably 5% water in the CO2 flue gas. So when we cool down the flue gas down to ambient temperature, the liquid water will be knocked out from the CO2. So CO2 at the saturated point. That is fine for the cycle operation. We don't have to get bone dry CO2 in order to run the cycle. However, if we try to export CO2 to CO2 pipeline, we have to meet the CO2 pipeline standard, which means we cannot have too much moisture into the pipeline to get the corrosion. So the standard way to do that is to use the MOSIF, remove the water, and then go into the CO2 liquefaction and purification unit. So that's a short answer.
Thanks. I see that there is a question number 2, but it's more again. This is probably not related to just direct combustion, but it's about modular units and finished gas pipework. So probably again, the guy here designing the plants. So Matteo, can you look at it?
Yeah. Modular units are my my task. I think I go quite sure on this question because it is not related only to supercritical CO2 cycles, but to all the modularized items. So if you go modular, the most you finish in the workshop, the better it is. Okay, so I would say 95% of the piping has to be finished in the workshop. Obviously, it's a must to leave some welding at site to be done, because you know, pipes are generous, we say in Italy, but not as much as they should. So you cannot stretch them too much, obviously. So you have to leave at least 5% of the welding on site. But in the modularized solution, the most pipe works use weld and test in the workshop, the best it is. And I say, I've seen in the last 5 years that many customers for different technologies ask us to make what we call the fit up of the modules in our workshop. Fit up means that you build up the plant in the workshop in advance, I mean, putting all the modules nearby, and you complete more than 95% of the pipe works on site, and also of the electrical installation, so that you know, the welding at site are really reduced, and this save a lot of time in installation. And obviously, if you go to critical areas where you cannot find you know, proficiency in welding, or it is really high costing, whatever you can do in the workshop, it's cheaper and it works better.
Thanks, Matteo.
You're welcome.
There are 2 more questions. They keep going at you, Xijia. So
Not a problem. Let me refresh.
Can you share the questions? Basically, can you share a bit of the experience or lesson learned? Yeah, basically about the heat exchanger operation, because the turbine is not yet there in Laporte. So how did you manage heat exchanging in the pilot?
In the past test campaign done in Laporte, Texas, we're able to test all the key piece of equipment, including the heat exchanger. So we're able to plot the temperature profile, which is very similar to what we predicted in the model. We're able to get the higher temperature and 300 bar pressure. So on the turbine, we work with the previous turbine OEM. We really have a lot of lessons learned and really achieve a lot of great achievement, actually, complete combustion, and also we're able to get turbine synced to the grid. The reason we go to the Baker Hughes really because once we get into the commercial phase at this point, we think strategic partner on the turbine OEM is very critical. Number one, Baker Hughes and the power line of sight on the same vision. Number two, we're able to levelize the extensive experience on the turbo expander design and the manufacturer from Baker Hughes. And also not only turbo expander, but also all the key CO2 compressors and pumps, et cetera, et cetera. So they're able to supply all the BOP turbo machinery, really helps us to drive the technology into the next phase. So that's the reason why we announced the JDA, the Joint Development Agreement with Baker Hughes for the technology development, and also they're the investor of Net Power. Really, we can create a win-win situation between 2 companies. So I think that is kind of quick and short answer on this question. So.
Thanks. I'll take the last one and I'll ask it to Joshua. And I'll turn it a little bit around. So thanks, John, for the question. So of course, no, we always talking about the turbo machinery, ramp rate, blah, blah, blah. But then we have these massive lumps of metal in the system, which are now driving inertia. So what do you plan to do in San Antonio to understand how the overall behavior of the system is driven by the behavior of a single component? So in this case, how heat exchangers are limiting or in other ways characterizing the performance in terms of transient response of the overall technology.
Yeah, so thank you for the question. And specifically speaking about the STEP project, our high temperature recuperator is a printed circuit heat exchanger. It is one of the largest, I think it is the largest heat exchanger of its size at the pressure that we are using it, a 265 bar on the high pressure side. It weighs almost 60 tons. I mean, it is massive. It's one of the largest pieces of equipment other than our process heater. So yeah, it actually can help drive some of those ramp rates. And I think really what we have to do is a little bit more research. So, I mean, one of the STEP project goals was to work through some of these first of its kind technologies, especially with like a high capacity recuperator. We want to try and prove out, we actually selected the PCHE heat exchangers because they have high efficiency, but in the long term, if we need a faster ramp rate, if you're going to have a very oscillating cycle, or if you're going to have kind of like a peaker plant where you're changing load frequently, you'll make different selections around your pieces of machinery and equipment based on how you expect to operate. So, I mean, I go back to kind of a steam turbine reference. It's very rare that you would ever put a steam turbine as a peaker unit, because once it gets up and running, it's very efficient. You want to keep it there at its most efficient point. So it really depends on what you expect your plant operation profile to be. So if you want to have a peaker unit as part of an sCO2 cycle, then yes, you will probably select something different than a PCHE heat exchanger that will allow faster transient temperature changes so that you can modify your cycle as needed.
Thanks, Joshua.
Sure.
I suppose we are running over 2 minutes. So personally, I would like to thank all the presenters and panelists for being here and sharing their insights on sCO2. I would also like to thank Jitka for setting this all up and driving it, and all you that attended for being here with us. I mean, those that are left and did not leave us along the way. Hopefully you enjoyed the webinar, and you got some piece of information that you will share in your organizations. Thank you so much.